Now clearly there are 4 other inverse trig functions that you could differentiate, and the derivations of these formulas can be done using the similar manner that we did for arc cosine and arc sine. I strongly recommend that you give that a try on your own, but when you do that, you're going to find these are the formulas that are going to come about. Notice some symmetry here. Always when we do the inverse cofunction, sine to cosine, tan to cotan, secant to cosecant, the only change is the negative, right? Positive versus negative. They all have a 1, they all have a u squared. When you're subtracting them, you end up with them inside the square root. Notice that the order of the subtraction switches from sine versus secant. And when you're adding them as it works out, there is no square root in the final answer. And then there's also this extra little factor of u inside the absolute value bars for the arcsecant and arccosecant. And the absolute value is there simply to make sure that we're in the right quadrant. It's just how it works out based on the domain restrictions of the inverse trig functions. So a few things to memorize for sure, but you know, a lot of similarities there too. So if you can follow those patterns, then it maybe won't be so bad. All right, so for each one of these, we have to consider the chain rule. And so that means that, for example, if I take the derivative of the arctan of root x, we know that the argument is root x, or x to the 1/2. So that's going to be part of our answer, right? The argument never changes, but don't forget the chain rule. Or in this case, we're just going to replace u prime with the derivative of this. And so that's going to work out to be 1/2 x to the negative 1/2 in the numerator. And then in the denominator, we have 1 plus u squared. 1 plus u squared is going to be 1 plus x. And sure, I suppose we could leave the answer like that, but it's probably nicer to simplify this a bit. So nothing stays on the top, right, except for the 1. The 2 drops down to the bottom. The root x drops down to the bottom. And then the 1 plus x stays on the bottom. And that's it. And if we try this with the arcsecant, well, the arcsecant has a similar sort of pattern here. We have u prime, which is 2, over the absolute value of u, which is 2, the absolute value of 2x. And then we have the square root of, just be careful here, make sure that when we square 2x, you're squaring both the 2 and the x, so you get 4x squared. So we get 4x squared minus 1. And yeah, you can factor out the 2 from the absolute value. So the 2 over 2 reduces to 1. The x still stays in the absolute value because that could be a positive or negative value, right? So we want to make sure that we keep that answer positive. And that would be the final answer there. Great. All right. So now we've got this one right here on the left is kind of a scary looking problem. So let's see what this one does. If we take the derivative of this mess, well, let's see, we've got a 1/2 out front. So that's going to be multiplied by the whole thing. And then we've got a product rule right here, right? U equals x and v equals 1 minus x squared raised to the 1/2. So u prime equals 1 and v prime equals 1/2 1 minus x squared raised to the negative 1/2 times, don't forget the chain rule, negative 2x. And that actually simplifies a little bit. We've got the 2's go away, so we have a negative x times 1 minus x squared to the negative 1/2. So that's a little bit of scratch work for the product rule here. So u prime v is u prime times v plus u v prime, that's u, times, I'll go ahead and use parentheses, negative x times 1 minus x squared raised to the negative 1/2. All right, and that's the derivative of the product here. I shouldn't close that parentheses yet because everything's being multiplied by the 1/2. And then we have the arcsine. The derivative of the arcsine of x is 1 over the square root of 1 minus x squared. All right. Okay, so actually, come to think of it, this 1 minus x squared shows up everywhere, but I don't really like writing it like this when it's written in other ways, in other places. So let's actually rewrite this using exponents instead. This is 1 minus x squared raised to the negative 1/2. All right, so that means that we can factor out a 1 minus x squared raised to the, well, the smallest exponent between 1/2, negative 1/2, and negative 1/2 is negative 1/2. So what's left? Well, if we factor out, if we subtract negative 1/2 from this exponent, we get 1. So that's 1 minus x squared. And then we've got minus x squared, right? X times x is x squared. We've got a minus sign right here. And then we're factoring out all of this. And then all of this goes away as well. So this is times 1, which we don't need to worry about, but we also have a plus 1 that we do have to worry about. All right, cool. So then we're going to see that some things go away because we can combine like terms here. 1 minus x squared plus 1. Actually, nothing cancels out, does it? We have 1 plus 1 is 2, and negative 1 minus 1 is negative 2, but that's okay. We can factor out that 2, and it's going to cancel out with that 1/2. So we're going to get 1 minus x squared raised to the negative 1/2 times 1 minus x squared raised to the positive 1, and these are the same base with different exponents, so we can multiply the two terms together by adding the exponents. So negative 1/2 plus 1 is positive 1/2. So what are the odds that this thing works out to be a nice clean answer like the square root of 1 minus x squared? Okay, so now you can imagine that there is a way, perhaps a complicated way, but a way to start with this as an integrand, and then when you integrate it, you end up with this as your final answer. Something to chew on for sure. All right, and this last problem is going to be, we can approach this two different ways. The direct way would be to say, well, this is the sine of u, right? U equals the arc cotangent of x. Okay, so that means that the sine of u differentiates to the cosine of u. The argument never changes. So the arc cotangent of x. But don't forget the chain rule. We're going to multiply by the derivative of our argument, which is going to be negative 1 over 1 plus x squared. All right, that's the derivative of the arc cotangent. And I suppose we could leave the answer like that. Or we could say, well, the cosine of the arc cotangent. Well, let's see. If some angle theta has a cotangent of x, then we have the square root of 1 plus x squared as our hypotenuse. So if we're going to take the cosine of this, we're going to have x over the square root of 1 plus x squared, and then we're going to multiply that by negative 1 over 1 plus x squared. And we can actually combine these together and get negative x over 1 plus x squared raised to the 1/2 plus 1 is 3/2. All right, so that's one way we could do the problem. Another way we could consider doing this problem is simplifying the expression first. This is the same thing as the derivative of, well, the sine of the arc cotangent is 1 over root 1 plus x squared, or 1 plus x squared raised to the negative 1/2. And then we get rid of all the trig at the very beginning, and then we just use inverse, we use power rule, right? So negative 1/2 gets pulled out front. The argument of 1 plus x squared never changes, and we get negative 3/2 because of the power rule. But don't forget the chain rule. We multiply that by a 2x. And we're just about done. We just have to remember that the answer will reduce a bit. The 2's are gone. There's a negative. The x is still there. And then, wait a second, this is exactly the same thing we got when we used the other method. So these are the same. That's cool. It's relieving, in fact. If we do the problem two different ways and we get the same answer, then I'm feeling very confident that this is the correct answer.